Hello and welcome to this FMSP online revision recording for the MEI specification module D1 Decision Mathematics. And this topic is graphs. So let's have a look at the specification and see what it says under the heading of graphs. Well, there are two sections. The first really is all about definitions, and the second refers to using graphs to model problems. Now then, I'm going to quickly remind you of each of these terms. Nodes and vertices. That's the names we use in graph theory for points. Arcs and edges. Names we use for lines between points. And node order, or degree of a vertex. That's the number of lines coming out of a point. The number of edges coming out of a vertex, I should say. And then types of graphs. Simple graphs. A simple graph has no loops and no repeated edges between the same pair of vertices. A complete graph has all the possible connections between pairs of vertices. We use Kn to denote the complete graph with n vertices. A connected graph is one in which there is a route from any vertex to any other vertex over a sequence of edges. Graphs which are not connected are usually fairly obvious because one set of points is in no way connected to another set of points. But check out the first example I'm going to do from an exam paper in just a moment. Bipartite graphs, it's in the name. Bipartite, two parts. This is one where there are two distinct sets of vertices, and any edge can only go from a vertex in one set to a vertex in the other set. Now then, three words that I have to think about very carefully. Walks, trails and paths. A walk is a sequence of consecutive edges. A trail is a walk where all the edges are distinct. In other words, no edge is repeated. And a path is a trail, in other words a sequence of consecutive edges with no repeated edges, where every vertex is distinct. So it's a trail where no vertex is repeated. A cycle is a loop through vertices along edges and it gets back where you started. A Hamiltonian cycle is a cycle which visits every vertex exactly once and returns to where it started. A tree is a graph in which there are no cycles. A digraph, that's a contraction of directed graphs, and it's usually fairly obvious because you see arrows on them. And planarity, a planar graph is one which can be drawn so that no edges cross. Now a word about modelling. You probably recognise the situations in this list. I certainly recognise Königsberg bridges, but typically in an examination question you have to use a graph to model a situation which you've not met before. So let's do a couple of exam questions. And can I remind you that if I read the question very quickly, or if you need to go back and see a question again, you can always rewind and pause the recording to read a question. So here we go, we have a graph. Consider this graph where all the arcs are straight lines. Explain how you know the graph is simple. Well, that's fairly straightforward. First of all, I can see there are no loops from a vertex back to itself. And a simple graph has no loops and also no repeated edges, and again I can see there's no place where one vertex is joined to another vertex in two different ways. There we go, there's 2 marks for that, 1 for each statement. Now on to part 2. Explain how you know the graph is not connected. Well, at first glance you might think it is connected, so I'm just going to break out the highlighter and show you that it's not. I notice B on its own over here. I'm just going to follow that route from B. B goes to F, F goes to A. A's connected to D, but there's no other connections. So there's a little set of 4 vertices there which are not connected to the other 4. Let's change colour, just make sure we can see that absolutely clearly. So E's connected to H, H is connected to C, C is connected to G. And none of those 4 vertices are connected in any way to A, B, D or F. There we go then. I can see it's 2 distinct sets of points with no connections from one set to the other set. So this is what I've seen, that B to F to A to D is in no way connected to my other set, which if I start at E is E, H, C, G. Well, that's good so far, but I want to make it really clear using the right notation. And what I've got is 2 distinct sets of vertices. It might be a bit smarter to list them in alphabetical order. A, B, D, F is not connected at all to C, E, G, H. And there are 2 marks for that part of the question, one for spotting what's going on and making it clear, and the second for identifying the 2 distinct sets of vertices. Okay, let's have a quick read of questions parts 3 and 4 before I move on to the next slide. On a copy of the graph, add as many arcs as you can whilst keeping the graph both simple and not connected, and then give the number of arcs which you have added. Notice 3 points here. And then for part 4 of the question, imagine that a new graph is produced in which 2 vertices are connected in my new graph if there's no connection between them, directly or indirectly, on the original graph. How many arcs would this new graph have? It's only 1 mark. We haven't got to draw it, we just have to think about it. Okay, let's move on and do those 2 parts then. So here's the copy of the graph, but before I go racing ahead and drawing lines on it, I'm going to think very carefully about what I already know. I know that D to A to F to B is a little distinct set of points. It's a subgraph which doesn't have any connections to the other 4 vertices. I'll just sketch the other one as well. I have E to H to C to G. So here's my other distinct set of 4 vertices, and I'm going to think about them separately. Let's look at this first group of 4. Well, I could certainly add the edge AB. That doesn't connect it to the other 4 vertices at all, and I can put in any other connections that are missing within this group of 4 vertices. So I can add AB, BD, DF, but I can't add any more edges because I've now created K4, the complete graph on 4 vertices, and adding any more edges would mean the graph wouldn't be simple. Now let's look at the second group. Well, once again, in exactly the same way I can add 3 vertices to this to create another little K4, and the edges I'm adding, I may have just said adding vertices, I meant adding edges. I've added the edge CE, EG and GH. Well, there we go. Now at the moment what I've written will only score 1 mark out of the 3 available, because it does say draw them on the graph. So let's do it. AB, BD, DF, CE, EG and GH. And I must say, given the graph on the left looks quite complicated, I'm glad I thought about it first. This scores another mark, but don't forget there was another part of the question which says give the number of arcs which you have added. So I better state that as well. 6 arcs have been added. And that assures me of the third mark for that part of the question. So now on to part 4. Imagine. Imagine the graph which is made up of connections, which it's not quite all the connections that aren't in the first graph, but it's all the connections which would connect points unconnected in the first graph directly or indirectly. Gosh, I've got to get my head around that, so let's just see what were those points. Well, we had a set A, B, D, F which were connected to each other, and quite distinct from that was the second set, C, E, G, H. So if I want to draw a new graph where edges are only drawn if they connect something from this set to something from that set, well, how many ways can I do that? There are 4 choices for a vertex from this set and 4 choices for a vertex from the second set. I think there's 16 possible edges. There's a second way of thinking about this, which I rather like. If you like combinations or combinatorics, perhaps you will as well. There are 8 vertices in total, and to draw an edge you have to choose from 8 2 vertices. So 8 choose 2 is all the possible edges. Now you're only allowed an edge if it connects a point that's not in any way directly or indirectly connected already. So it's got to be a point from the left hand set with a point from the second set. So if I do 8C2, I'll count too many edges. I don't want to have a pair from within the set A, B, D, F. In other words, if from that set of 4 I choose 2, I don't want any of those possible connections. The same applies here. Choosing a pair from C, E, G, H is another 4 choose 2. So 8 choose 2 minus 2 lots of 4 choose 2 will give me what I want. 8C2 is 28, 4C2 is 6, and that gives me 28 take 12, which is 16. Of course, for 1 mark, you only need one or other of these 2 solutions. Okay, let's move on to a question which involves modelling. And my advice here is read the question very carefully, because all these modelling questions where you have to draw a graph to represent the situation are different. Make sure you've taken in all the information and reread the question after you've done it. So we have an electrical circuit with wires and switches and components labelled as shown. Draw a graph showing which vertices are connected together, notice either directly or indirectly when the 2 switches remain open. And I can see straight away A and E are connected already when the switches are open, and B is connected to C, C is connected to D, and I can get from B to D, so these 3 form a little group all connected to each other. How many arcs do you need to be added when both switches are closed? Well, we'll think about that in a moment. Let's look at the bit below. The graph below shows which components are connected. Well, all of a sudden we have a graph which perhaps looked new or different, but notice you've got A and E on the left, like you had over here. You've got B, C and D on the right, much as you have over here. So expect there to be a connection between the first and second parts of the question, and that's going to be important when we answer part 4. Now the questions are repeated on the upcoming slides, so let's do this in parts. First of all, draw a graph showing which vertices are connected. Okay, well, I've got A, I can see that that's connected directly to E. Then I have the other vertices B, C and D, and I've already checked out that directly or indirectly, in terms of an electrical circuit, you can make contact from B to C, C to D and B to D. So there we go. An attempt at it or some sort of method gets you a mark, and the graph that you can see there is sufficient for the answer mark. So that's the 2 marks for part 1. Now part 2. How many arcs need to be added to your graph when both switches are closed? Okay, so you now got a connection across there and a connection across there. Well, that means that A is connected to any of, well, I can get to B, C or D, and E can now reach D, but also indirectly B and C. Now I perhaps wouldn't do this in the examination, but just to make it clear to you, this is what we're doing. We're saying A can be connected to B, A can be connected to C, and A can be connected to D. When the switches are closed, those connections will exist. Same here. E to B, E to C, and E to D. In other words, the possible new connections are A to B, A to C, A to D, and E to B, E to C, and E to D. Well, that means 6 arcs need to be added. You've probably noticed already that this makes K5, which we saw in the second part of the question, so there is going to be a connection. Just to comment that some sort of method, maybe this list of vertices, is needed for the question, but you must say how many arcs are added to get the second mark. So, perhaps this graph isn't so dissimilar to the circuit question we've already done. Let's answer part 3. Find the minimum number of arcs which need to be deleted to create 2 disconnected sets of vertices. Write down your 2 separate sets. Well, this was my initial thinking. I could try separating A from the other 4 vertices. That's a 1-4 kind of split. I could separate A and E from the other 3 vertices, a kind of 2-3 split. Then I thought, well, if I start saying A, B and E and make a 3-2 split, surely that's the same as a 2-3 split. So 3-2 or 2-3 doesn't make a lot of difference. I thought I'd investigate those 2 and see what I thought. So I'll start by isolating vertex A. And I picked A as an example. If I were to isolate A, I'd have to cut all 4 of those lines. So I'd have to delete or cut AB, AC, AD and AE. And because every vertex is connected to 4 others, doesn't matter if I consider A or any other vertex, I get the same answer that I'd need to delete 4 arcs. Well, maybe that's the answer. Don't know. I'm just going to consider another situation then. What if instead I wanted to separate A and E from the rest? Well, I'd have to cut the full. Let me see, what can I cut? I have to cut this one, those 3. Don't have to cut AE now, but I'd have to cut E off from anything. So I think to isolate A and E, or the set of points A and E, I'm going to need 6 cuts. Well, I can't really see that I'm going to get a better answer than my first. So splitting it into 2 sets I can do with 4 cuts, and that's the minimum number of arcs, and that splits it into a set A and all the rest, B, C, D, E. And just to comment that for 3 marks you need some sort of evidence that you've tried to do this, but in particular you need to show the 2 distinct sets that you've created, as well as stating how many arcs need to be cut. On to part 4. Explain. Explain why in the second electrical circuit it might be possible to split the components into 2 disconnected sets by cutting fewer wires. Well, that's interesting, because originally there were only 2 open switches in my original diagram, and it was separated into 2 sets, AE on the left and BCD on the right, with just 2 open switches. Why was that? Well, it's because in the electrical circuit some of the connections were indirect. Okay, I'm going to try and write down something that links this part back to the first part of the question. A and E were isolated from B, C and D in part 1 by 2 open switches. It certainly beats 6 cuts, which is what I'd have to do, but I've got to explain, and I think the explanation is because there were routes via other vertices. In other words, what they've elsewhere called indirect routes, rather than by a unique edge. So it paid to spot that the last part of the question, or the second half of the question, was linked to the first part of the question. A and E were isolated by 2 open switches because connections were possible via to other vertices by indirect routes, rather than there always having to be a unique edge to be cut. There we go then. I hope that's refreshed your memory about graph theory, and don't forget to check out the rest of the recordings in this series.